Hello everyone, this is Tian Marie Barangco of BSEC 3C, and for today's video in our Communications 2, we are going to design binary machines and find its probability of occurrence for each variables. And we will also compute for entropy using probability method and Hartley equation methods. So first, our given data is from my name, but it will only compose the first and the last name. So it is going to be LEEBARANCO, and combining similar letters and arranging it alphabetically, it is going to be ABCELNOR. And for the first case of our binary machine, we're going to have 4 questions, which is equivalent to for 4-bit. And we're going to stick with a problem that asks about what is the sixth letter of my given name if it isn't arranged alphabetically. So the answer would be R in this problem. So in Q1, it is asking if it is A, B, or C, or E. And if it is true, equivalent to 1, so true is equals to 1 and false is equals to 0. So if it is true, then it will ask if it is A. And if it is true, then A would have a probability of 0.25. And if it is false, it will ask if it is B. And if it is true, then B would have a probability of 0.125. And if it is false, then it will ask about C. And if the value is C, then the probability would be 0.0625 and so on. And in here, if the question that is asked would be, is it A, B, C, or E, then the answer will be false. Then it will automatically ask to the second question, which is it L? And if it is true that L is what is asked, then the value would be 0.25. If it is false, then to the next question. Q3 asks if it is N. Then if it is true that N is what is asked, then the probability would be 0.125. And if not, then move to the next question, which is it R? And if it is yes, then R would have a value of 1, which means it is true, and the probability would be 0.625. But if it is false, then O is the answer. Here is the probability equivalent. So the variables are, we have 8 variables, and these are their probabilities. The number of bits is based and determined by this, which is if it is A, then 1, 1. If it is B, then 1, 0, 1. If it is C, then 1, 0, 0, 1. If it is R, then it is going to be 0, 0, 0, 1. And computing for entropy. Entropy is equals to H, which means eta in Greek. So using probability method, we're going to find the summation of the variables that has a probability of 0.2 and multiply it by the bit number or the number of bits. So we have here a total of 2.75 bits. In using the Hartley method, which is equals to H, negative summation of probability times log of 2 times the probability. So summation, for example, in the probability or the variables that has the probability of 0.25 is 2, and then log of 2 times the probability. So the total would be 2.75 bits. For case 2, which is our second binary machine, we have 6 questions, which is equals to 6 bit. The first question is it is A or B. So if it is true, then it would ask if the value is A. And if it also is true, then A. A would have a probability of 0.25. And if it is false, then the answer would be B with a probability of also same with A, which is 0.25. And if it is false, then it would ask the second question, which is it C? And if this is true, then the value of probability in C is 0.25. If it is false, then it will ask the third question, which is it E? And if it is true, then E would equals to 0.125 probability, and so on. So here, the given the probability of their occurrence. And the number of bits is also determined as the same process that we did on the first binary machine. And computing for entropy using probability method, we will also perform what we did on the first binary machine. So the total in here is 2.46875 bits. And also in using the Hartley method, the final answer is 2.46875 bits. So it is equal. So we can use either of these formulas. And for the summary, in binary machine 1, the entropy is 2.75 bits. And the binary machine 2, the entropy is 2.46875 bits. The maximum entropy is measured by the formula of eta is equals to log of 2 multiplied to the total number of probabilities. So it is 8. So the H max or the maximum entropy is 3. Now solving for the code source efficiency, which is actual entropy over maximum entropy, equals to 2.75 bits over 3 bits, which is 0.9167 efficiency. And for the binary machine 2, the total efficiency is 0.8229. So from here, we can assume that binary machine 2 is more efficient since the lower the efficiency rate is, the more efficient our machine would be. In code source redundancy or RE, the formula is 1 minus the value of efficiency. So 1 minus 0.9167 in our binary machine 1, the redundancy is 0.0833. And in binary machine 2, the redundancy is 0.1771. And in this case also, we can say that binary machine 2 is better in redundancy, since the higher the redundancy, it means that it is possible for us to maximize the transmission. And here are the key points in determining their contrasts. So in binary machine 1, it has higher value of entropy, and binary machine 2, it has lower value. It is less predictable in binary machine 1, and binary machine 2 is more predictable. Binary machine 1 is low probability and more random. In binary machine 2, it has high probability and is less random. And also, binary machine 1 needs more information to be transmitted to get the desired outcome. And in binary machine 2, it only needs less information to be transmitted to get desired outcome. So all in all, binary machine 2 is better. Binary machine 2 has lower efficiency result, which means it is more efficient. And machine 2 has greater redundancy result, and it means the transmission will be maximized.